Okay. What?
Why are you recording this?
Because then kids are going to have questions on the problems and say, hey, you can just look it up. Okay? Pretty soon I'm not even going to come to school anymore.
You're just going to do it at home.
Yeah, just do it at home. Just commute from home. Or what do they call that when you, not commute from home, what's that called?
Work from home?
Work. Yeah, that's it. Work from home. That's what it is.
Wow.
There's something fun that it's called though when you do that. Like home office or I don't even know what. Anyway, do these come out to be the same?
Well, that should be a home classroom.
Do these come out to be the same?
No.
Yeah. Good.
How did you just divide?
Okay. Yeah, I just divide them. So I'm going to go 2 divided by 4 and 2/3. So I'm going to really take that and go 2 divided by, here, I'll do it well.
2 divided by 3.
What is 4 and 2/3 as a decimal? 4.66666
repeating.
Okay, so that comes out to be 0.42 whatever. So we'll just remember that. Okay, so I need to compare that with 3 divided by 7, and that comes out to be pretty much the same thing, 0.4285714. It gets different after that, but close enough. And then 4 divided by 9 1/3 is 9.3333333. You get to have all those 3's in there, and that comes out to be the same also. Okay, so since those all come out to be pretty much the same, that means that yeah, you can see they're all the same, and they're fancy stuff. So that means that they are proportional. Okay, so final question, is triangle AED similar to triangle ABC? Yes.
Can we do 14?
Yep, we sure can.
And then 15, 16?
Can you be more impatient? Probably you could.
I think she could.
Okay.
Okay, shut up.
All right. 14 is a little bit tricky because of the way they have the triangle set up. Okay, what you have to be able to do with this one is figure out what side goes with what in these triangles, and the key is in the similarity thing that they write. They said triangle ABC is similar to triangle DBA. And then I'm going to put on here the A, B, whoops, and C, okay? So we need to figure out what sides go with what, all right? And the way you do that, like I said, is by looking at the way this thing is written right there. So AB, what's the length of side AB? 3. That goes with side DB. What's the length of side DB?
No.
So it is N, okay? And that's going to equal, now look at the last 2 letters in each one, BC, which is Y, divided by the last 2 letters on this one, BA, which is 3.
Nice.
He's saying BA, it's funny because it stands for something funny that you do.
Nice.
He's showing his maturity. Yeah. Is BC 4? Did I write it down wrong?
Yeah.
Oh, that's not a Y, that's a 4?
Yeah.
Okay, sorry, that makes things a little bit easier.
Oh.
Okay, so this is 4, not a Y. I can't read my own writing. Okay, and then that also equals, thank you, if I look at the first and the last letter, AC is 6, and that goes with the first and the last letter on the other one, DA, which is M. Okay, so those are the proportions that you use to figure that out. And so this one was tough because the way the triangle is set up, it's hard to know what side goes with what. You actually have to take this triangle and rotate it a little bit to get them to match up. Okay? But now that we have this, we can solve for both of these. To get MI cross multiply, 3 times 3 is 9, divided by 4 is 2 something. And then to get M, I do the same thing. I cross multiply. 3 times 6 is
18.
18. Divided by 4 makes something.
It's 4.2 something.
Yeah, 4.5.
I was close.
You were close.
I was calculating in my head. I'm not
Okay.
smart.
All right. Does that make sense how I did that using the letters here and the similarity statement? Yes? No? Somebody say something.
Yeah. Sort of.
Okay, good deal. Sort of. I'll take it sort of.
I would have been saying this.
Yeah. Get used to it. Get used to it. It's spring sports.
I know. Is there always something you're going to
I'm going to be gone starting after spring break. I'll be gone, not so much for you guys, but 6th period. I'll be gone close to once a week. A couple times for you, because like when we go and play Ridgefield, we got to leave at 1 o'clock. So
Why?
you know, it's a 2-hour drive.
Good.
All right, number 15. So we are starting with this shape here, and they very nicely give you the
Good. We have to graph
coordinates
this one.
of each point. Yep, you did have to graph this in order to solve it. And it says, draw its dilation by a scale factor of 3. What do you think that means?
Multiply by 3.
Multiply all of the coordinates of these points by 3. So instead of this point being at 2, 2, it's now going to be at 6, 6. And I'm not even going to be close to fitting this on my thing, am I?
No.
All right, it's okay. We have the technology. Okay, let's try that. So I was from, let's see, the first point was 2, 2, and then 2, 6, right? And then this one went from 2 to how high? 2, 5, thank you. And then this goes there. Okay, so this point right here has the coordinates of 2, 2, so that's going to go to where? 6, 6, because if I multiply each one by 6, that is what I get. So I'm going to put a new point at 6, 6. Okay? This one right here was at 2, 5. Now it's going to be at 6, 15. Okay? And then this one right here goes from 6, 2 to what? 18, 6. So that is going to be right there. And so my new shape, if I connect those points, is not surprisingly, once again, a triangle. The question is, what is the ratio of the perimeter of the dilated triangle to the perimeter of the original triangle? So perimeter, of course, is distance around, right? So how long is this segment right here? 4. This one is 3, and so we can use the Pythagorean theorem and figure out that this one is 5. Okay? So the perimeter of that will be 3 plus 4 plus 5, which is 12. Okay? Now I'm going to compare that to the perimeter of the new shape. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Does that surprise you that the length of that is 12? No. Because what do we do to the coordinates of all the points?
Times it by 3.
Times it by 3, so we times the side length by
So
3 also.
guarantee it's going to be 9.
So this is going to be 9, and this one is
15.
going to be 15. Okay? So the perimeter of that one, 9 plus 12 is 21, plus 15 is 36. How do the perimeters compare?
They're times by 3.
3 times as much. Again, not surprisingly. Now here's the exciting part. What is the ratio of the area?
I don't know.
Not 3.
Not 3.
Oh.
Okay? What is the area of this little triangle? 6, because 3 times 4 is 12, and half of 12 is 6. What is the area of this big triangle? 54. 6 times 9, 54. How many times bigger is this than
9.
that? 9 times. Can anyone tell me how you can dilate by a factor of 3 and get an area that's 9 times as big? It's what? It's not cubed because it's area, so it's
Squared.
squared. Awesome. So since area is square units, if my scale factor is 3 or my dilation factor is 3, to figure out how the areas compare, I have to square that number. So if my dilation was 4, how much bigger would the area be? 16, because 4 squared is 16.
10.
Then it would be
100.
100, okay? So to figure out how the areas relate, you have to square the dilation factor, okay? All right, let's do another one. Whoa. Oh, all right, so this one goes all the way to 14.
By the way, thanks for doing the Santa Claus yesterday.
Yeah.
Yeah.
I just did 3 of the problems.
I just kind of kept rolling there. I was all fired up. I had it going, but no.
I realized you're like, yeah, I just did so.
What I didn't tell you guys is that when I first did the practice test stuff, I got the very first problem wrong. So I had to delete that video, go back and restart it.
Nice.
Well, I need you guys. I need your help. All right, so this point right here is at 2, 2. Then the next one is at 0, 12. Then I have 14, 6. And finally 10, 12. 10, 12? Yeah. Okay. And so this gives me this crazy quadrilateral.
Nice.
Like that. And what are we doing?
I think it was at the button.
I got to go back to the point I started at. And what are we doing to the points this time? Or what are we doing to the shape this time? Okay, scale factor of 1/2, so we're going to cut them all in half. So instead of this being at 0, 12, it's going to be at 0, 6. Instead of this one being at 2, 2, it's going to be at 1, 1. This one moves from 10, 12 to 5, 6. And this one goes from 14, 6 to what? 7, 3. You guys understand where she's getting those numbers from? Yeah? Okay, so that gives me this new shape right here. And we just have to answer one question on this, right?
Yes.
Is the dilation similar to the original quadrilateral? Yes? How can you tell? What has to be true for shapes to be similar? The angles have to be the same, yeah. So all the angles are the same. And then what has to be true about the sides? They have to be proportional. And since we cut all these points in half, what will be true about the ratio of the sides? They'll be half. Okay? So yes, they are similar.
No.
Okay?
What's the last part of 18?
What's that?
What's the last part of 18?
The last part of 18. Are all isosceles triangles similar? No, because they can have different angles. Are all right triangles similar? No, because they can have different side lengths and different angles. How about all isosceles right triangles?
Yeah.
Yes, and that's because of that thing that we talked about. What are the angles in an isosceles right triangle always? 45, 45, 90, so the angles will always be the same. And then the sides will be x, x, and x times the square root of 2. And so that means that the proportions will be the same as well, no matter how big or small the triangle is. Okay? Okay, why don't you pass those forward?